some thermocouple theory. These terminals here where the thermocouples join are what's known as the cold junction. The measurement of a thermocouple is determined by the difference in temperature between the hot junction and the cold junction. This is expressed as a voltage in millivolts or even microvolts. The little Maxim chip here measures that voltage and determines what that means in degrees C. However, to do that, it needs to know the temperature of these terminals here. This is what's known as the cold junction compensation. It does this using an internal temperature sensor that is basically measuring the temperature of the chip and assuming that the terminals are exactly the same temperature. Invariably they're not, and this is probably one of the most significant sources of error in any thermocouple measurement system. To minimise that, I've mounted the chip as close as possible to the terminals. I've run a ground plane under the chip, and although I haven't been able to get the ground plane into the terminal block itself, because I wasn't that ambitious, I've got reasonable coupling. Nonetheless, I'm seeing in that prototype that I showed earlier an error of maybe 1.5 degrees, 2 degrees between the two. Now, if you're running a furnace or a kiln, that's not a problem. If you're measuring room temperature, that's significant. So this is an experiment to try and resolve part of that by improving the thermal coupling between the chip, the Maxim sensor chip, and the circuit board. I don't know if this is going to work, but it'll be fun finding out. I mean, the whole thing's been an exercise in fun. It's not been as though I actually need a 16-channel thermocouple multiplexer. I don't know of anybody who actually does, really. You look at the package, and it seems to sit pretty flat on the board, and it does. However, there is a tiniest of gaps between them. So what my experiment involves is to put the smallest blob of silicone grease that I can manage onto the ground plane just where the chip mounts. Now, I'll make myself a tool out of a bit of old SMD tape. Oh, that's heaps. What I want to do is, that's about the sort of coverage I want to get, where a little bit of grease will fill the gap between the chip and the board, hopefully improving thermal coupling to the board. And therefore the cold junction temperature should be a little bit more accurate. It's a theory anyway. Don't drag the iron lead across there, Philip. So yes, that was about the most exciting part of the assembly there, putting that bit of grease on there. Everything else should just go smoothly here. And you can probably almost fast forward the rest of it. Which corner will I approach? That one's a nice one. It never works out, it always jiggles. I should just have to go in close here again. I don't want to get any of that grease on the pads. That's not good. But that's what flux is for. For those of you who don't know, flux is actually there to clean the board. And by cleaning the board and the component leg, it facilitates the process of tinning. Well, this is turning into quite a treatise on solder, isn't it? Nearly there. That's near enough for government work. Some more flux. Wow. This is the challenging one because it's got that capacitor close there. See, I was compromised there because I always feel with decoupling capacitors, especially in analog circuits like this, which are low voltage, measuring microvolts, you get all your decoupling capacitors as close as you can to the board. Oh, I think we're there. Okay, so that's all the surface mount assembly. The connectors are, I might do some more on the connectors later, but now I'm going to have a rest.